Right, good evening, good afternoon. Very few students, but only the best one are here. I hope the one not here will hear this. Okay, let's remember what we have done last week, even though we are going to do something slightly different today. Importance sampling is something I introduced last week because it will be necessary at one point today. It's useful, maybe you will see it in a different context when you have a distribution and you would like to get another one from this one. So it has many applications. Now I just remind you once more, the system we consider is always the same. It's a discrete dynamical system. The system at times n+1 is given by xn plus f of xn n. You can put these two things together, it doesn't really matter. Here it's useful because you can think about this as a small perturbation of xn. And we have a model error. In the note I have changed with n as an exponent because last time I used it as an index. And the observation is a certain function of xn, it can also depend on time, plus an observation error. And in general, f and h are functions. Later on today, we will use them as, just there, there will be matrices. So this h is called the observation operator, and f gives us the dynamics. Now, what is the idea about all this? We have some observations, y. And this is a notation meaning we have y1, y2 up to yk. We have k observations. And then we can, there are three different types of things we can do. Either having a certain number of observations, we can try to predict what is going to happen with h. So, no, not with h, with x. So predict xn for n bigger than k. This is a prediction process. Or we can look at xn for n very close to k. This is called the filtering process. So you do the observation and the prediction almost simultaneously. Or you can do what is called the smoothing process. You have observations and you look at what happened before or find an initial condition which gives you the best observation or what is very close to observation. I will come back to this today also. But most of the time we use this filtering process. This is the mostly used approach. And sequential data assimilation is when precisely you first focus for the system at time n having the previous n-1 observations. So this f is for focus. So you predict xn knowing the n-1 observation. And then once you get the last one, so when you get the last observation at time n, you update xn and you get what is called xn analysis. So it's always a game between focus and analysis. And then we have just look at a very special situation, and please be very careful when you use Kalman filter because it has many assumptions, and if you don't check them, then you can use it in a non-appropriate way. So first, evolution is given by a matrix applied to xn plus a shift. The observation operator is also a matrix. We assume that this model error is Gaussian centered at 0 and with a certain covariance Q. We assume that the observation error is also Gaussian centered at 0 and with a certain covariance R. And the initial condition is also given by Gaussian. We have many assumptions. Once you are in this framework, you can write explicit formulas for, or it's called a closed formula because we can write it explicitly. It's a product of many matrices. You can write a formula for xn focus and then for xn analysis once you have the last observation. And in this formula, there is something called the Kalman gain matrix. It's just a certain product, but it will reappear later. And by the way, if you look carefully at this formula, you wouldn't be surprised that they can all depend on n, because it's an iterative scheme. So in fact, this D could be n-dependent, this H could be n-dependent, as long as they are matrices. This Q could be n-dependent, R could be n-dependent, and B as well. Simply at every step here, instead of having just these matrices without an index, you can have an index, but the structure is the same. There's no surprise. All right. Oh, good evening. At least we have one person online. Oh, two. Can you hear me? I was not sure. Yes, can you hear me? Or somebody? I have no answer. Can you hear me? Okay. I cannot do anything. So today I have my goal. I have two goals. First, very quickly speak about this. Why very quickly? Because as we can see, without a concrete model, we cannot do so much. I mean, we can build the theory, but not do something so concrete. The next section will be about particle filter, and I like it, and I will tell you why. So I want to spend more time on particle filters. But nevertheless, I want to speak about this one because it's also related to something we have done probably in the second lecture. It's a generalization of something we have done in the second lecture. So it's good to look at it again. Okay. So what is this? So this variational approach it's a smooth, I just erased it. It's a smoothing process. So it means we have some observations and we look at the initial condition in the past. So it's a smoothing process, which leads the best initial condition. So I will explain with a picture first. And I did already a picture like this. Let's say this is T0, T1, T2, up to a certain Tn. We have the time here. Suppose we have this is the previous forecast. We had a previous forecast. Now we are here. This is a present time. We have some observations. So we have observations up to time n. And we are going to look for better initial condition. So we are going to use both this point and the red one to improve something. And then we can do also some predictions. So this is a corrected forecast after observations. Which, if you look at page 15 of my notes, in fact, we had already studied this, and I introduced it with the least square method, which will be a special case of the formula I'm going to introduce. So this is the idea. We have an initial knowledge, we have observation, and then we update We find the best initial condition which fits with the data, with the observation, but then we can use it to focus something. So we consider the model. We consider a perfect model in the following sense that the dynamical system is just x of n plus 1 is f of xn. No model error. We can implement it. We can implement some model error, but I look at it and it's really more complicated. So I just don't do it. And consider H from Rn to Rm. I do not assume that it is a matrix. So I'm going to write xt0b. Maybe I can write this xt0b is this point, xt0b. And this b is for background. So this xt0b, it's a point in Rn. Be our prior knowledge. The system. So at time t0, even before the observation, y at time t0. So once the observations are available, we define a cost function. The cost function. I introduced the notion of cost function already 2 weeks ago. It's a function L from Rn to R. What is important for cost function? It's a real valued function by L of x is this formula. Okay, so this is one term. So x is going to be what we look for. So it's the initial point that we want to find. This is x. So with this term, we measure first, in a sense, the distance between x and xt0b. And so it's a vector, horizontal vector, a matrix, vertical vector. So it gives us a scalar. It's quadratic in x. And then we have a second term, plus 1/2 sum I is equal to 1 up to n of h. So something we have already seen. In fact, I could simplify a little bit the notation. Again, there is a matrix or inverse of a matrix. And what we have the evolution of X. Then we use this observation operator to make it comparable with the observation, Ty. And sorry? B? I'm going to say, I told you these are two matrices. Because if we look, and they are not of the same size, just observe that this is in Rn. So it means B is an n by n matrix. On the other hand, this is in Rm, and m is usually smaller than n. So it makes R a m by m matrix. And with y T1 up to Tn, the observations. Now, what is B in, oh no, let me keep this picture for a second. So R is called, it has a name, R is called, and I already used this name, observation error covariance matrix. And B is the focus. No, I prefer the background. The background covariance matrix. And just make a remark. If you take R is equal to the identity matrix, and if you forget B, so you put it, its inverse is just the zero matrix, which means the first term does not appear, then we have the expression for the least square. Precisely on page 15, a couple of weeks ago, I already mentioned something like this, which was the special case of this expression when this is the identity matrix, which means when you have the identity matrix, you are just measuring the norm square of this guy, and the first term was absent. So this is a generalization. Why we introduce these two matrices? The idea is the following. Depending on your system, depending on your measurements and so on, you are maybe not so confident in these points. Or you are not so confident in this initial condition before any measurement. So you can decide, you take a decision before, or if you trust more this initial knowledge or this background information, or if you trust more your measurements. And again, also the measurements you can decide, because it's a matrix, some components are maybe more reliable than some other one. You can decide, you have a lot of freedom, depending on what you want to study. So by choosing or by tuning R or B, you can put more importance on the initial condition or more importance on your observations, right? And then what we do, so once you have decided who are B and R, then we look for X, minimizing L of X. And there are methods for this. I don't develop at all this method, but there is this, what is called the gradient descent method, or the other one, one is called the Gauss-Newton algorithm, or the nonlinear conjugate gradient method. You can check this on Wikipedia, you can find information, but I just wanted to give these names. So once you minimize this, we get x t0 as a solution. This minimizing problem. And then what we do, and then compute f any iteration of x t0 or any, which means once we have this one, okay, let me take. Now we have found this point. This is going to be x t0 now, the result of this minimizing problem, and precisely we draw this curve, and we can forecast the evolution of the system in the future. Because it's not really important to do it here. We have observations here. Nevertheless, this picture is misleading. Why is it misleading? Because of dimensions. Probably the observations are in a space of smaller dimension. So you don't, I should draw the curve. I mean, probably there you have additional information in an orthogonal direction. This is, it's sometimes called the observation plane, because this is in a picture in M, where you have the observations, but X contain more information because it's in a space of most probably of higher dimension. So this, what you can see here is in fact, maybe we should call it H of Xn or something like this. What is visible is a projection on this space. Yeah, this is a little bit misleading. But okay, what I wanted to say is we can generalize this least square method by putting these two matrices B and R, which they give us more freedom. We can decide what is more important, if we trust more the observations or if we trust more our initial guess. And then we do it by small, here I put 6 or 7 time, but we can do it by smaller patches of observation, or it's called windows, the window of observations. And then when you have, let's say you have focused something, later on you have observation and you just repeat the method. Now, as I said, this minimization problem is in itself a problem, but you can do it. And in the notes, I have also written, I don't want to do it, I want to concentrate on the second part. What we can do, and also write X is X T0 background plus H, and assume that H small, whatever it means. Yeah. X is so X is really the variable you want to minimize as a, so it's a function, or it's one variable of a function. X T0B is this point. Yes, or The background knowledge, yes.
And then like X zeros and
Now this is going to be the new variable. So this is what I'm going to do. What I can do is a kind of Taylor expansion. So I suppose that this initial condition is not too far from this one. So I write it as a small h. Then in the long expression, you do a Taylor expansion. You keep only the term linear in h, so it gives you a polynomial of degree 2 because you have two dependencies on h, and you can simplify some expression. So we can write h small and do some Taylor expansion. In terms of small h, and you end up with a slightly different formula. L of h is equal to something, and then you try to minimize this as a function of h. So it's just a different point of view. Probably it's simple. The minimization problem is simpler because you have simpler expressions, because you have already done a Taylor expansion. Some formulas are written in the notes. And the last remark in this section, I don't have a clear application for this. I guess we should really take one model, write this long formula for the cost function, and then differentiate it and find its minimum, but it's certainly a long process. I know that for weather forecast, they use this technique, but they have already done once for all the computations with a very complicated model, and then they just need to implement the data. But it's a huge process. The final remark, and I already mentioned it, if you don't want to have an exact model, so what you can also do, so it's a final remark. You can consider, and first I wanted to do it, but it's really more complicated. We can consider xn plus 1 is a f of xn plus a certain model error. However, if you do it, here we have a minimization problem with respect to one variable. If you do this because psi n is not known, you end up with a minimization problem with respect to n variables, which is more complicated. So minimization with respect n variables. N is how many observations, so the size of the window. N variables, and this is more complicated. So it is possible, but I don't see the point of presenting it here. All right. But it exists. You should know that such things exist. If necessary, it can be applied. All right. So yeah, this picture, we should be a little bit more careful because in X, we have more information than in Y, usually. So now we can start this new section. And as I wrote in a message, I like it because it's quite natural. And probably next week, I can really present a concrete example on which I worked. I did a work about COVID-19 and this particle filter. So I think if you want to see something concrete where we can really explain everything based on what we have seen, I can present it next week. So 3.4, I will tell you more at the end. Particle filter. By the way, particle here has nothing to do with particle in physics. I don't know why it comes from, where it comes from. No, I know a little bit, but don't think about a particle in physics. So this is a method based on an ensemble predictions. So we are going to have many predictions. Plus what I explained last week, this importance sampling. We are going to use these two things. So if I just add one more sentence, we are going to have numerous predictions are made. And the best one, whatever it means for now, the best ones will be selected. Okay. So the framework is always the same. So it's very different from the Kalman filter because I don't assume any linear things or any special form. So the framework is always the same. Xn plus 1 is Xn plus f of Xn n plus this model error, and Yn is always h of Xn n plus observation error. This is always the framework. I don't assume anything. And just one more remark. I did it also last week. I'm going to suppose that at every n, we have an observation, which is not a restriction, because if we have less observation than update of the system, you just update your system freely L times and then put the observation. So what I'm saying is not a restriction. Having an observation for any n is not a restriction. And I already wrote something like this. Yes, on page. Sorry?
Do you think psi epsilon to be small?
No, we don't need to assume. No, we don't need. Of course, probably if they are very big, then we face a problem somewhere. But I don't have to assume it. And even more, what would mean small here? I have no way to measure what would be small. So it's not. I'm not going to do an expansion in terms of a epsilon or something like this. But probably, and okay, I will come back to your question when we know more. See page 58, I have written something saying that if you have less observation, then we just iterate the model freely. So this section is divided into two parts. The first one is called SIS. Importance. Something. So consider an initial condition. Following distribution. This is your initial guess. You have a system. You don't know the initial condition, but you suppose that it follows a certain distribution. It can be a Dirac delta distribution. So it means, let's say it's one-dimensional. So it can be that your initial guess is your system is really located here, Or you can say, I know that my initial condition is within this interval according to a Gaussian. So this is what you know about your system at the beginning. You do an initial guess about the initial condition, but it can be anything. And then you take a sample. Take a sample. So I take x0 j for j from 1 up to a certain number. J can be large. Take a sample x0 following this distribution. X0. So it means if you have a Dirac delta function, if you suppose only one value as an initial one, then you're going to take j times the same one. If you suppose that you have some distribution like this, you take some values a certain number of times. You take j initial values distributed according to this distribution. It can be a Dirac delta function. Please, if you have any question, if something is not clear, interrupt me. Otherwise, it's not interesting for you and it's less interesting for me. So we take this sampling, this sample, oh, probably it's a sampling according to this distribution. By the way, this family of x0j, j from 1 up to j, is what we call a realization. Realization of this pi 0. Now, set and define some weights W0j all equal to 1 over j. I'm going to associate to each initial condition a weight, but for now it's everywhere the same weight. So the focus at time 1 is given. I'm going to give it by the family x1j w0j. Be careful, I put a 0, so let me emphasize it, because it's a focus. J from 1 up to j. And who is xj1? It's just the evolution of x0j by this. So xj1 is this x0j plus f of x0j. It can depend explicitly on, oh, there is a mistake in the note. This is a 0 here, it's not a j. It's a time 0 plus xi 0 j. So I just, this is the evolution, and I take x0, no, x1j as the evolution of x0j by this formula. And I associate still the weight 1 over j. Right? And this is all id random variable. So it means every time I use this, maybe Gaussian or whatever, but it gives me a certain number. Okay. And now, what I can do with this So I have a family of points with a family of weights. These weights are not so interesting, but anyway, they will be more interesting in the future. For any G from Rn to, remember I use this because I don't know if it is a R or if it is Rn or a vector or matrix. It can be anything. With the expectation of x1 is defined by x1 f, because it's a focused g of x1 f. I give it by this sum over j from 1 up to j w0j. Again, I emphasize this is focused, and for focused, I use the weights at the previous time. And this is quite natural. We had a set of initial conditions. We let this set of initial conditions evolve. It gives us a set of the system at time 1, and we have no reason to prefer any of these points. So we have put the weight 1, the same weight, so 1 over g. And now I need to say what, so this is the focused before any observation. But now I'm going to use, I suppose that y1 is available. Once y1 is available, we set. So W, the weight at time 1 associated to the, it's called a particle. So the particle is indeed this x, this is a particle. This xj, we have j particles. So this weight at time 1 is given by wj 0 time I'm going to explain. I will give an example. So again, you observe that the denominator is just a normalization. And this function here is what we call the likelihood. I will give an example in a second. But we have already seen such a formula precisely for the importance sampling, or yeah, importance sampling or sample. Example. By the way, I agree. This first factor is the same for everybody, so I could factor it out. But after the next step, so after the first observation, it's not going to be the same anymore. So I just keep it. So yeah.
Don't always add up to 1.
Yes, this is why we have chosen this denominator. So indeed, remark, the sum of all these W1j, if we sum over j from 1 up to j, is 1.
It's like an updating, like which thing is more important.
Exactly. So let me give you an example. And if you look carefully, I have written that it follows the idea of importance sampling on page 53. For example, if we assume that yn is h of xn plus epsilon n. So I simply erase the explicit dependence here, and I will assume that the En follows a normal 0. And this is quite natural assumption that your error follows a Gaussian. So this is not so strong. Then is pi y of y1 knowing xj1 is given by the following formula. It's 1 over 2 pi m over 2 1/2 the determinant times this exponential of minus 1/2 . And now, indeed, so what you observe, these x1j are different. They depend on your how you chose x0j at the beginning, and there is some randomness in each of them because of the formula for computing each of them. So probably some of them will be further away from y1, and some will be closer. So when they are quite close, if you think about it, when this is small, the weight is big. It's close to 1 because it's exponential of minus thing. Exponential of 0 is 1. Exponential of a big number is very, very small. So if this number, or if this, I mean, when you do this computation, if this projection of xj is close to y1, then you have a big number, so you put a big weight on this particle. When these two numbers are, it's two vectors, but when you compute this, if these two things are far away, then you are going to have a weight which is very small. So this is how you focus on particles which have a big weight. And this is a general formula. I'm simply not assuming that it's Gaussian, but whenever you have a certain model for the noise or for the observation error, you can implement in this formula. So at least it's more or less explicit. So let me just say what I mentioned. The weight W1j is small if this h of x1j is far from the first observation. Right? And now I keep. So now we have computed these weights at time 1. Then set the expectation g of x1 analysis is given by the sum j from 1 up to j of this new weight W1j. X1j. So you can compare these two formulas. And the only difference is here you have 1 because you have analysis. And indeed, this weight is estimated by using the information on the first observation. So it's a very natural approach. And now you iterate. So I'm going to give the general formula. Because once we have this, okay, let me write it explicitly. After some iteration, we have a family of x, j at time n with, I have written n plus 1, it doesn't, no. So after some iteration, we have this, which lead us to xn analysis, because it contains already the information about n observations. This is computed. N observations. So I give you now the process for an arbitrary n, then we get j is always 1 up to j. We get x n plus 1 with first the weight n j. And this is going to lead us to x n plus 1 focused. And how we get this one is nothing but x n j plus f of x n j n. Hope there is no mistake. Yes, plus xi n j. So I'm just using now the dynamical system to get this point. And I don't change the weight from the previous time. And this is a focused at time n plus 1 with these weights. When the next observation is available, when y n plus 1 is available, set, I compute a new weight, w n plus 1 j no, there are n plus 1. And I need to divide by, I need to normalize it. So I divide by the sum. And let me stress something now, it's important. See, I keep this factor here. I could not put it and just compute the weights without this. But why we keep this? Because we want to keep the history. A particle which was good in the past has already a good weight, a big weight. So this makes this particle already good at the very beginning. And then I update it with this term. If I forget this, it means that I forget what happens before, and I don't keep track of the history. So we need to keep this. This term, keep track of the history of the particle. So now I write it of the particle xjn, or this n is, I should write just xj here because it's a history, so it's for different n. Or I can write x1 up to xn, 1 up to n. It keeps tracks of this. And now, once I have this on the blackboard, I can just write the general formula. The expectation of xn focused, or n plus 1, because it's written as n plus 1 focused is given by this sum of omega, or omega jn ng of x n plus 1. Also is the sum j from 1 up to j from 1. Okay. Is it clear what we are doing? And do you feel that it's natural or not? So if I try to make a picture, again, we have the evolution. This is a true evolution. So our system, true evolution. Sometimes it's called the truth. True evolution. I do some measurements. So these are, sometimes I have good ones, sometimes they're not so good. These are observations. And I have different particles. So I started with an initial condition. I let it evolve with the system. And I do this for many initial conditions. They can cross because they live in a space of higher dimension. This is a projection. And what we do, here we cannot see the weight, but at every time step, I associate some weights, which can be, you can represent them as the distance between the particle and the observation. And you decide how important is each particle. So it's important to keep the history because a particle which was maybe not good at the beginning can suddenly become good, but it could be an accident. So you really keep first track of the history and then you modify it. So it's a clever algorithm. Unfortunately, it doesn't work. Why? Can you guess why it doesn't work so well? We never know the truth.
And we have nothing to actually compare it against.
No, you can, I mean, like I did it in the very first lecture or second lecture, you can, they do it. I mean, they create synthetic observations. So they really create the truth artificially, and you can check if your algorithm works well or not. So there are methods to check if it works well or not. But even with this, it doesn't work well for the following reason, is that if you do this, most probably the weight, it will concentrate on one particle. So most of the weight will be 0, except one. or very few. And then if this particle is even moving away, since it has already all the weights, it becomes unstable. So you need to correct this instability from time to time. So for a short time, it works well, but not for a long time. For a short period of time. Works well. Usually works well. But then most of the weights will be zero, will be about zero, and one or two will concentrate, everything will be close. One. Of course, both cannot be close to one because the sum is one, but I mean, one or two will be close to the unit, so 1/2 or one, which means that the system is very unstable. You need a large diversity, you need many particles for your system to be stable. So when everything is concentrated on one or two particles, it's not good. And it can completely break down. So we need to correct this. And there is a way to do it. And this is the second section, which uses the same approach, but we do a correction. This is called the sequential importance. Resampling. This reason it's called SIR. And it has other names, also called. Bootstrap filter or condensation. What is the idea? We keep the same idea, but sample when necessary. Of course, we have to decide what means necessary. All right. So in a sense, when this problem is coming, so when the weight is concentrated on too few particles, we need to do something. I need to define a way to measure this when necessary. So I'm going to define set J and F, EFF, and this is for effective. We define it as 1 over the sum J to J. I take the sum of the square of the weights and the inverse. And observe. So this is called the effective sampling. Very simple. Observe. At the very beginning, when all weights are equal to 1 over j. If all weights are equal to 1 over j, what is this effective number? You have n times 1 over j square, so it makes j times 1 over j square, so it makes 1 over j. So altogether, you get that this j and f is essentially j.
Yeah.
Yes or no?
Yes.
J times 1 over j square.
So when they weigh equally,
No, it's an observation. If they are equal, we have this number. But if one of them is about 1 and all others k and are about 0, so the extreme case, then becomes 1. Is j and f is about 1. So it means this is one way to measure how these weights are distributed. And it's an easy way because when you do, of course, you implement this on the computer, it can easily compute this number. So it means I prefer when the weights are well distributed than when it's in this situation. So if I compute this number JF effective, and if it's becoming too close to 1, I need to do something. This is the idea. So this says KNF, the way, it's an easy way. It's not very precise, but it's enough, is an easy way to measure the uniformity. They don't have to be all equal to 1 over j, but you want to know if they are close to 1 over j or close to 1 having everything, the uniformity of the weights. And so what we do, so the SIR model consists in SIS plus resampling, and I need to explain what it is. Whenever this effective number is smaller than a certain alpha times j. And again, you have some freedom. So in the book I'm reading, they take alpha is 1/2. What I've done is alpha is 1 over 10. Is alpha equal either 1/2 or 1 over 10 or any fixed number. And this is something you choose for some reason, but you put a condition in your algorithm. If this number is smaller than alpha times j, then you do something. And what means is you do something. So I will be in the situation when this condition is met. So suppose is WN, oh no, not W. This JN effective is smaller than alpha times G. And observe that we have the following thing. No. Okay. Okay, sorry. I subdivide zero, one into a certain number of intervals. And I'm not fully sure, so let me just think. Yeah, we have the weights. I have a doubt now. No, but it's like this. Okay, so of course, all weights can be different. You have J weights, but if you subdivide this in some intervals, in each interval, you have a certain number of them. All right. And I represent in fact, I should represent more, the values here, but it's easier to look at this, at them like this. So what I'm going to do, in a sense, I want to eliminate these weights because they are, no. Now I have a doubt.
I think we actually want to eliminate those. I think we want to eliminate those that, like, let's say if everything's like only at one interval, then we throw that one away.
Okay, I can just copy my notes, but now I don't really understand. Let me first explain with words. What we do, we want to keep the particles which are close to, or which have big weights, eliminate the other one, and put an weight 1 over J to all new particles. So we want to make all weights equal. So, but I have a small problem how we implement this now. So let me first write it with words and maybe we can just come back to it. Yeah.
Maybe it's not a good idea to say the new particles to be J. Maybe you should write as G prime so that we know that it's like the new quantity after.
This is exactly what I do. But what I don't really remember now is if we choose for the weights or if we choose for the particles. And no, it's the weights. Exactly, because the particle are, but no, we need to fix the particle. We have to choose some of them. But we cannot choose which one we. So let me write on. So there is a missing part. Maybe just keep a few lines. So when we are here, choose among, but the way we choose is what I'm for now missing, which is among the particles a subset or a new set. X prime or xn k or k. For k, again, from 1 up to j, and associate weight let me write one or two more equations, and then maybe we can find out. As I said, we take some particles, but we allow the repetition. So it means some particles, I'm going to select them certainly more than once, but it doesn't matter. But I take among these particles a certain number of them with repetition if necessary, and I associate a weight 1 over j. And with this, so if we do it carefully, with this, we have, it's important. So this is the initial formula for computing the analysis at time n, but with the new, you're right, it's not a good idea to keep the same letter. So I should write z. In my note, I have written z. dn. And if we do it cleverly, wait, I just finished the formula. It is the same as the sum j from 1 up to n, to j. This new, okay, so now I need also a new letter for this. Oh, no, I can keep this letter. No, because in this is the previous number. So I should not, otherwise there is a contradiction. The weight just 1 over j to all of them. This is some 1 over j, g of zj. So what is the aim? And now we can try to reconstruct this part. What is the aim? I'm going to among the set of particles, I'm going to select some of them, maybe more than once, according to the distribution. And then I put the new weight 1 over j to all of them. And if we select precisely this carefully, this quantity, what we expect, will not change. And this is precisely the goal of to do it cleverly. When we compute this expectation with the previous weight of the particle we had, we obtain the same number with this 1 over j and this new particle. There's still one part missing, but I can just continue. Now, we set, I couldn't do it before, but now because I have already computed this, we set this is equal to 1 over j. So now I give a new value. Before it was the value we had before the resampling, but now I set 1 over j. And we continue. SIS model until J, and now it's a new number. I need to put JK F is smaller than alpha J for K. It's certain bigger than F. So the idea is you do the same process when the weights are becoming not enough uniformly distributed. You resample and you do it in a clever way so that your expectation stays the same, even with this new weight. And then now all your weights are 1 over J, and you continue the process until you have again a new warming sign saying, oh, the effective number of particles is becoming too small. So you do this process. So what is missing is this point. But okay, let's try to find together. When you have a distribution, precisely if you take values according to this distribution, so if you take a sample according to this distribution, then if you put the quantity 1 over the same weight 1, you get with your sample this distribution. So this is the point, but I need to express it more carefully. But it's the same. When you have a sample, when you have a distribution, you can think about this as a distribution. You sample it. So it means you just take arbitrary values according to distribution. Then your expectation is the same as with the initial one. So I will try to make it more precise next time, but I just wanted to give you the feeling. We have these weights, this distribution of weights. We collect the particles. Or maybe I can do a picture of this now. The process. Wait, I just do this picture. We have the truth and the particles moving too far away. So at a resampling, this is resampling. What we are doing, going to eliminate this one. And we are going to duplicate. We're going to start anew from here. And the same if another one is too far away, we are going to eliminate it from this vertical line. We eliminate it. And we are going to duplicate maybe this one. And they will not overlap. Of course, they overlap at time 0 at this time, but because there is a random process, there is a term psi n at each step. Already after one step, they will not overlap anymore. So you need some randomness for this algorithm to be effective. If it is a deterministic algorithm, then you would have just 2 times the same particle, and this is not interesting. But if you have some randomness, after one step, they will already diverge or be different. And precisely as I mentioned, if you take it cleverly, the expectation with the previous weights and with the new weights give you the same value. So you do it coherently. So I will just try to make this part a little bit more clear next time. But yeah, it's this idea, you have a sample, you have a distribution. If you take a sample according to this distribution, then with this sample, you keep the same expectation. Okay, and the last remark I have written is that in fact, this approach can be even used for in your system. In the initial equation, I have written xn plus 1 is xn plus f of xn n Let me keep some empty space plus xi n. So up to now, I have written this. But suppose you have a parameter theta, which can depend also on n, which you don't know. You can compute this parameter with this approach. How? Because you create enough particles. You create enough particles with different values of theta. And then the one with a wrong theta n will just move away at a certain point. On the other hand, the one with the right theta will, or you expect that they will stay close to the truth. So you're going to eliminate the particle with bad theta, and you keep only the one with a good theta, and then this is the way you can select and find out the parameter theta. So I will present a concrete application next week. I think it's good to have really a concrete example before we move to something else, because this is quite efficient. The problem with this approach is consume quite a lot of data. I mean, if you want to do it very carefully, you have to have a lot of particles. So you need to be careful how you implement it. Otherwise, it takes a long, long time. And indeed, in the application I did it, the computation took too long. But okay, so I will try to just make it more clear, but I hope you understood the idea. And it's a rather naive approach, but it's quite efficient once you have enough resources for the computation. Is there any question or remark? Silence. Do you have any remark? Yeah.
So any of this data is like to select the way to select the data we measure to find the valid one, like valid for resampling.
Yeah.
So how to find this data? Like
no. If in your model there is a it will come in the application I'm going to present next week. But suppose you have a parameter and you have no information. So you just take particles with, okay, you choose that this particle has a theta is equal to 1, this one has a theta equal to 2, and this one has a theta is equal to 3. Okay, you fix it. For this particle, you say this one has theta is equal to 3. And you observe that, oh, with theta is equal to 3, it's moving away from the truth very quickly. So you can get that theta is not 3. Now, you see that theta is equal to 2 or theta is equal to 1, they are close to the truth. So you let your system evolve longer, but maybe the one with theta equal to 1 will still move away. On the other hand, theta is equal to 2 will come or will stay close to the truth. So this way you get some information that theta, you had no idea about it, but you can say, oh, it's probably the one with theta is equal to 2 are the best. So you fix theta is equal to 2. So this is the vague idea of how you can use this process for finding an unknown parameter. But yeah, you need enough particles to have many possible values of theta and select like this. But I will present one clear application next week. So we can use this for finding unknown parameters. Here, the parameter does not depend on time, but you can even do it with a parameter which depends on time, but then you need even more particles, because at every time you need to do all possibilities. Okay, that's all for today. Thank you.